Introduction to WebSphere MQ. This unit provides an overview of IBM WebSphere MQ. It introduces the business requirements that led to the development of WebSphere MQ, positions it against other forms of program-to-program communication, and discusses the function it provides for building business application solutions. After completing this unit, you should be able to explain the positioning of messaging and queuing in today's business environment, provide a high-level view of WebSphere MQ functions, and describe the breadth of coverage of WebSphere MQ products. One of the biggest challenges in IT today is increasing diversity. As the focus on integration increases, the boundaries extend beyond the individual enterprise to include partners, suppliers, and customers. It is this diversity in IT environments that is increasing the complexity of the challenge that a company like yours has to deal with. This is where middleware comes in. Middleware is infrastructure software that simplifies the problem of horizontal integration. The infrastructure has to tie together people, data, and applications across and beyond the enterprise to provide benefits throughout the value chain. Infrastructure middleware provides the operational resilience that allows your organization to react quickly to necessary business changes and to adapt dynamically in this new business world. The WebSphere platform provides the software foundation for on-demand business. WebSphere started as a transactional application server and has grown with customer needs to provide software products delivering a breadth of business integration. While it emphasizes the value of the entire platform, IBM also allows the customers to start simply, using just the functionality required at the time, and then to progressively add functions as needed. The IBM middleware platform is implemented as a service-oriented architecture, SOA, which IBM calls the IBM WebSphere Integration Reference Architecture. WebSphere MQ is message-oriented middleware that provides the reliable, proven messaging backbone for SOA connectivity. So why are interfaces so expensive to build and maintain? There are several reasons. An application's interface logic is usually intertwined within the application's business logic. This is due to the nature of the applications themselves. The programming models don't allow the separation of interface logic from the applications themselves. And the more tightly integrated the interface, the more difficult the application is to change. As you add more connections to your program, the application becomes more and more complex. Over time, and with enough separate connections, the interface logic can in fact exceed the business logic. In those circumstances, reuse becomes difficult and impractical. SOA is the architecture for solving this problem. The objective of SOA is to reduce the service down to the bare business logic. Service-oriented architecture, or SOA, is not a new concept. It is the next step of a connectivity evolution that has been going on for some time, and indeed, we have already solved much of the problem with existing technologies that you may be using today. Message queuing takes us one step in this evolution by separating or decoupling the connectivity logic from the business logic of the application program. The decoupling of two programs provides assured delivery that the data arrives safely at its destination queue, and once-only delivery, ensuring that a single copy of the data is sent. Let us begin with a simple concept, passing data from one program to another. In traditional program-to-program communication, Program A and Program B must be directly connected to one another. But what if we decoupled the two programs? Instead of directly communicating, Program A writes its data to a place in memory, and Program B retrieves the data from that same place in memory. In WebSphere MQ terminology, the place in memory is called a queue. By placing the data in a queue, the information can be stored safely when the retrieving application is not available. Program A can write to the queue even if Program B is not running. Delivery can be asynchronous, meaning that the sending and receiving application do not have to run simultaneously. But what if Program B needs to send a reply to Program A? For program B to send a message back to program A, you simply create a second queue. Program B retrieves data from Q1 and sends the reply data to Q2. A synchronous application model is one in which program A sends the data to Q1 and then waits for the reply from Q2. This model assumes that program A and program B are running simultaneously, or program A might have to wait a long time. But what if a program A does not need to wait for a reply? Using the extended asynchronous model, program A puts a message on Q1 for program B to process. But it is program C, acting asynchronously to program A, which receives the reply from Q2 and processes it. Typically, program A and program C would be part of the same application. The asynchronous model is a natural choice for WebSphere MQ. Program A can continue to put messages on Q1 and is not blocked by having to wait for a reply to each message. It can continue to put messages on Q1 even if program B fails. In that case, Q1 stores the messages safely until program B is restarted. What does happen if program B fails? Typically, in WebSphere MQ, program A puts messages on the queue and program B gets them. If program B is busy or is not available, the messages are stored safely in the queue until program B is ready to get them. If at the point when B becomes ready, program A has completed its processing or has failed, it does not matter. Program B can still get the messages and process them. In fact, it is possible for the messages to safely reside in the queue even if the sending or receiving program is not running. The messages are time independent. Time independence works because the queues are not owned by the application programs. The queues are owned by a resource manager called a queue manager, in the same way that databases are owned by a database manager. There are three main styles of communication. In the conversational style of communication, two programs directly communicate with one another. It is the fastest form of program-to-program communication. If one of the programs or the interface between the two programs is not available, communications do not take place. APPC, CPI-C, and the sockets interface to TCP/IP are examples of this style of communication. The call and return style is similar, but when one program calls another program, the first program is blocked and cannot perform any other processing until the second program returns control to it. Remote procedure calls are an example of this style of communication. The third style of communication is messaging. In messaging, each program acts like a standalone program. Program A gets its input from one queue and sends output to another queue, without knowing that its output queue is actually the input queue of program B. The other programs are not aware of a failure of one of the messaging programs. The other programs continue to get messages from the input queue and send messages to the output queue. Let's look at communication styles in more detail. The conversational style of program-to-program communication requires that a communication connection exist between each pair of communicating applications. This style requires a great deal of communication interface code within each of those applications, and if one of the applications or the communication interface itself is unavailable, nothing happens. In WebSphere MQ, the communication takes place between queue managers. The application program writes to some named queues, and the queue manager determines the location of those queues and handles all of the communication. The MCA that you see in the figure is the message channel agent, which is the queue manager program that performs the network communications. This figure shows two systems, System 1 and System 2. Each system has a queue manager, QM1 and QM2. On QM1, Program A is going to send some messages using the WebSphere MQ interface, or MQI call MQ input. First, Program A puts a message to the locally defined queue, Q1, with the call MQ put. Then, Program A puts a message to a remotely defined queue, Q2, that resides on QM2. The MQI call is the same MQ put, but the queue manager, QM1, determines that Q2 belongs to a different queue manager, so the message is temporarily stored in a transmission queue until the message can be sent across the network to QM2. Now it's time to process those messages. Program B on QM1 issues an MQGet call to retrieve a message from Q1. Program C issues a similar MQGet to get a message from Q2. It's important to note that Program A was able to send messages to both local queues on the same queue manager as the program, and to remote queues on other queue managers. But WebSphere MQ programs can only read messages on local queues. There is no remote MQGet in WebSphere MQ. In order for an application program to communicate with the queue manager, the program must use the MQI. The MQI is a simple application programming interface that is consistent across all platforms supported by WebSphere MQ. The MQI protects applications from having to know how a queue manager physically manages messages and queues. The calls are divided into major and minor calls. Major calls are not more important. They are simply the calls most commonly used in any WebSphere MQ application. An application must first connect to its queue manager before it can access any resources by issuing an MQCONN or MQCONNX call. When the application no longer needs to be connected to the queue manager, it issues an MQDisk call. To access a queue or other queue manager resources, an application must first issue an MQOpen call, and when it no longer requires access to that resource, the application issues an MQClose call. Once the queue is opened, an application uses an MQPut call to write a message to that queue and an MQGet call to read a message from the queue. But an MQGet is not a simple read. When you get a message from a queue, the message is physically removed from the queue and only resides in the application program. That action is referred to as a destructive get. An MQ put to a topic string is used to publish information which can be sent to subscribers of that topic. The MQ sub and MQ sub RQ calls set up the subscription and the subscriber program that uses MQ gets to retrieve its subscription messages. The MQ put one call enables an application to open a queue, put a single message on the queue, and close the queue, all within a single call. The MQ begin, MQ commit, and MQ back calls enable an application to put and get messages as part of a unit of work. The MQ inc and MQ set calls are used to perform administration functions within a program, to inquire about the definition of an MQ object, or to change the definition of that object. IBM WebSphere MQ has two additional application programming interfaces: the Java interface for use in Java applications, and the Java Message Service, or JMS, which allows programmers to write event-based messaging applications. MQI and JMS calls are covered in more detail in Unit 2, Programming with WebSphere MQ. A WebSphere MQ message has two parts: a header or headers, followed by some application data. All WebSphere MQ messages always have a header called the MQ message descriptor, or MQMD. The message descriptor contains control information about the message that is used by both the queue manager and the receiving application. It contains a number of fields that you review later in this course. The application data can contain whatever you want, so long as it is computer readable. The data in a message can be traditional character or numeric data, or it could be digitized pictures or audio or video. The queue manager places no restriction on the kind of data, only on its length. A WebSphere MQ message has a maximum length of 100 megabytes. However, later in this course, you'll see that messages larger than that size can still be processed. One of the advantages of a messaging system is the ability to easily process data in parallel. Let's use this travel agency program as an example. To book a vacation, the travel agency must combine reservations for a car rental, an airplane flight, and a hotel room. The application sends messages to each of those companies at the same time and then waits for the replies to come back. When the 3 replies are received, the travel agency program can complete the transaction. Those 3 other companies, the car rental company, the airline, and the hotel chain, process thousands of similar messages each day. How does each company know where the reservation reply should be sent? Inside each message's message descriptor are 2 fields, the reply to queue and the reply to queue manager. These 2 fields are the return address that is used to direct the reply message back to its correct destination. Another advantage of WebSphere MQ is the ability to automatically start an application when a message is put on a queue and certain conditions are satisfied. This facility is known as triggering. Triggering can occur based on selected conditions, such as when the number of messages on the queue reaches a predefined number, or every time a message arrives on a queue. This figure shows the sequence of actions involved in triggering. Step 1. Program A puts a message on an application queue that is enabled for triggering. Step 2. If the conditions for triggering are met, a trigger event occurs, and the queue manager examines the process definition object referenced by the application queue. The process definition object names the application to be started, which in this example is Program B. Step 3. The queue manager creates a trigger message containing information copied from both the process definition object and the application queue definition. The queue manager puts the trigger message on a special local queue called an initiation queue. Step 4. A long-running program called a trigger monitor gets the trigger message from the initiation queue and reads the message. Step 5. Based on the trigger message, the trigger monitor starts Program B and passes it to the trigger message as a parameter. Step 6. Program B opens the application queue and gets messages from it. Another common application model in WebSphere MQ is the client-server model. In this example, the server application, Insurance Quotations, handles requests from multiple client applications. Each application client is identical and requests information from the application server. The server program sends replies to the correct client because the reply to queue and the reply to queue manager fields in the message descriptor provide the return address. What happens if the server program cannot handle the workload and the request queue begins to fill up? Start another copy of the server program. In WebSphere MQ, multiple applications can get messages from the same queue at the same time. A WebSphere MQ client is the component that allows an application running on a system without a queue manager to issue MQI calls to a queue manager running on another system. The client stub receives the parameters of an MQI call from the client application and sends them over a communications connection to the server connection. The server connection is on the same system as the queue manager. The server connection then issues the MQI call to the queue manager on behalf of the application. After the queue manager has processed the MQI call, the server connection sends the output parameters of the call back to the client stub, which then passes them to the application. Most MQI calls and options are available to the client application. The application simply issues an MQCon or MQConX, where supported, to connect to a queue manager. Special consideration of WebSphere MQ client and database units of work are discussed later. Not surprisingly, a reliable communications connection is required. Some implementations of the conversational style of communication support implementation of a distributed unit of work using a two-phase commit protocol. A two-phase commit allows simultaneous update of two databases at the same moment. Using this single distributed unit of work can be both resource-intensive and complex, and only works if both applications and the network interface are available at the same time. WebSphere MQ, on the other hand, offers a simpler solution involving multiple units of work acting asynchronously. The WebSphere MQ solution is shown in the lower half of the figure. The first application writes to a database in sync point, puts a message to a queue, a.queue, in sync point, and then issues a call to commit the changes to the two resources. The message contains data which is to be used to update a second database on a separate system. As the queue is a remote queue, the work is committed and the message becomes available for retrieval by the sending MCA. In the second unit of work, the sending MCA gets the message from the transmission queue and sends it to the receiving MQA on the system containing the second database. The receiving MCA then puts the message on the destination queue. In WebSphere MQ, channel communication is always performed as a unit of work, so that no message is ever lost or duplicated. When this unit of work is committed, the message is available for retrieval by the second application. In the third unit of work, the second application gets the message from the destination queue and updates the database using the data contained in the message. It is the transactional integrity of units of work 1 and 3, and once and only once, and assured delivery properties of WebSphere MQ used in the unit of work 2, which ensure the integrity of the complete business transaction. Security is an important aspect of system management. Security features of WebSphere MQ are covered in more detail later in this course, but here's a brief overview of some of the security features that WebSphere MQ provides. Authorization is based on user ID. A queue manager can check whether a user is authorized to enter administrative commands or to access WebSphere MQ resources within a program. If the user is not authorized, the command or the MQI call fails. An MCA can authenticate a partner MCA before allowing messages to flow. The MCAs can be defined to encrypt the data before sending and decrypt the data after receiving it. A message descriptor normally contains a user ID field and other information about the originator of the message. This information is called the message context. Information in the message context can be used to authenticate a message and to check whether the sender of the message has the authority to access a WebSphere MQ resource on the system on which the message is received. The user ID might also be used by the application to check whether the sender of the message has the authority to access a resource that is not a WebSphere MQ resource, such as a database, but whether this is possible depends on the security features provided by the respective resource manager. You have now completed this unit. Having completed this unit, you should be able to explain the positioning of messaging and queuing in today's business environment, provide a high-level view of WebSphere MQ functions, and show the breadth of coverage of WebSphere MQ products.